Noether's theorem is a profound result in physics that links symmetries in physical laws to conservation laws. Here are several examples. 1. Time translation symmetry conservation of energy. Symmetry. The laws of physics are invariant, do not change, over time. For instance, an experiment performed today will yield the same results as one performed tomorrow if all conditions are identical. Conservation law. This symmetry implies the conservation of energy. The total energy of a closed system remains constant over time. Example. A pendulum in an isolated system continues swinging with constant total mechanical energy, the sum of kinetic and potential energy, assuming no friction. 2. Space translation symmetry conservation of momentum. Symmetry. The laws of physics are invariant under spatial translations, meaning they are the same in all locations. A physical process in one place behaves identically in another. Conservation law. This symmetry implies the conservation of linear momentum. The total momentum of a closed system remains constant. Example. In a collision between two billiard balls, the total momentum before and after the collision is conserved, regardless of where the collision takes place. 3. Rotational symmetry conservation of angular momentum. Symmetry. The laws of physics are invariant under rotations. A system behaves the same regardless of its orientation in space. Conservation law. This symmetry leads to the conservation of angular momentum. The total angular momentum of a system remains constant in the absence of external torques. Example. A figure skater pulling in their arms while spinning rotates faster to conserve angular momentum. 4. Gauge symmetry in electrodynamics conservation of electric charge. Symmetry. Electromagnetic theory exhibits gauge symmetry, specifically the invariance under changes in the phase of the wave function of charged particles. Conservation law. This symmetry corresponds to the conservation of electric charge. The total charge in a closed system remains constant over time. Example. In a circuit, the total charge flowing into a node equals the total charge flowing out, consistent with charge conservation. 5. Lorentz symmetry conservation of relativistic momentum and energy. Symmetry. Special relativity posits Lorentz symmetry, meaning the laws of physics are invariant under changes in inertial reference frames, e.g., moving at constant velocity. Conservation law. This symmetry leads to the combined conservation of relativistic energy and momentum. Example. In particle physics, high-energy collisions, e.g., at the Large Hadron Collider, conserve relativistic energy and momentum, consistent with Lorentz invariance. 6. Scale symmetry, dilations, special scale-invariant quantities. Symmetry. In some cases, physical laws are invariant under rescaling of length and time scales. While not universally true, scale symmetry is present in certain classical systems, e.g., idealized systems without characteristic length or time scales. Conservation law. This symmetry is linked to conserved quantities in systems that obey it. Example. In ideal fluid dynamics, the Euler equations exhibit scale invariance under certain transformations. 7. Kapton symmetry fundamental consistency of quantum field theory. Symmetry. The combined symmetry of charge conjugation, C, parity, P, and time reversal, T, implies the laws of physics remain invariant under these transformations. Conservation law. While Kapton symmetry itself doesn't directly imply a single conservation law, it ensures the consistency of particle interactions in quantum field theory. Example. Particle-antiparticle creation and annihilation processes respect Kapton symmetry. 8. Isospin symmetry conservation of isospin in nuclear reactions. Symmetry. Isospin symmetry in nuclear physics treats protons and neutrons as nearly identical particles under the strong interaction. Conservation law. This symmetry leads to the conservation of isospin in strong nuclear reactions. Example. Reactions involving pions, particles composed of quarks, conserve isospin quantum numbers. 9. U1. Symmetry in quantum mechanics conservation of probability. Symmetry. The Schrödinger equation in quantum mechanics is invariant under a global phase shift of the wave function. Conservation law. This symmetry ensures the conservation of probability, meaning the total probability of finding a particle remains 1. Example. The normalization of a wave function in quantum mechanics is preserved over time. Conclusion. These examples illustrate the profound connection between the symmetries of nature and the conservation laws that govern physical systems. This relationship reflects a kind of pre-established harmony in the structure of the universe, where fundamental principles, symmetries, dictate the invariance and coherence of physical laws.